Christopher here. Time for boring diagram explanation number 51. Number 51 is going to have to do with spectral lines, which is from topic 3. Okay, so the first thing that you need to know is what are spectral lines. So spectral lines show the shifting of wavelengths towards a certain end of the visible light spectrum. So that's pretty much what spectral lines are and what they do. So let's just finish writing this down and then we'll continue. Okay, next. So a key term that you're going to want to know to explain spectral lines and why they shift towards the red end of the spectrum when they're moving away and the violet end of the spectrum when it's moving closer to you. A key term to realize and understand is the Doppler effect, because this is what explains why the wavelengths shift to the ends of the spectrums when they're either moving closer to us or farther away from us. So spectral lines are going to be used in this case to be used as evidence for the Big Bang Theory. So we're just going to write that down because that's something else you should know. Are used as evidence of the Big Bang Theory. So spectral lines are used as evidence of the Big Bang. Okay, so now that we have all that down, we know what they are, we know what explains why they shift to the ends of the spectrum, and we know what they're used for, we're going to dive ahead into these models. So you'll see that the first one is labeled the standard spectral lines for any element. So what that's going to mean is that this is going to be the standard set of spectral lines that you're going to compare other sets like these two to know whether it's a red shift and it's moving away from us, or it's a blue shift and it's moving towards us. So this is the standard one. So we're just going to write that down. So this is the standard, and this is being used to compare the other ones too. So let's label all of these last four models as individual galaxies. This way it'll be easier to talk about them. So we'll label this one Galaxy 1, Galaxy 2, Galaxy 3, and Galaxy 4. Okay, so let's start with Galaxy 1. If we look at these, we look at the set of spectral lines that we're given, and we look at the standard set of spectral lines, you're going to see that they're in the same location, which is going to mean that this is not moving away from us or closer to us, because the wavelength is the same as a stationary object. So that would mean that this is stationary, so we're going to write no movement equals no change in location. So what that means is that it's not going to be moving and it's going to be stationary if there's no change in location of these spectral lines. So we're going to write stationary under Galaxy 1. Okay, so now Galaxy 2. If we look at the set of spectral lines we're given and the standard set of spectral lines, you're going to realize that they have shifted to the right end of the spectrum and towards the red end of the spectrum. So the red end of the spectrum contains longer wavelengths, and the violet end is going to contain shorter wavelengths. So that means, according to the Doppler effect, if you're getting longer wavelengths, that's going to mean that the object is moving farther away from you. So this is going to be called a redshift, and this is going to be moving farther away. So this one is going to be moving away, and you could tell because of the redshift. And that's a key term to know for the Regents or any other test you're going to be taking on this. So that redshift means that it's moving farther away from you. So let's take a look at Galaxy 3. We're going to see that Galaxy 3, in comparison to the standard spectral lines, the spectral lines are moved towards the left end of the spectrum and towards violet. So, as we know, violet contains shorter wavelengths, and red contains longer wavelengths. So we're going to know that since it's tilted toward the shorter wavelengths, shifted towards the shorter wavelengths, we're going to know that according to the Doppler effect, if you're getting shorter wavelengths, you're going to know that the object is coming closer to you. And this is referred to as a blue shift. So we're going to label that, if my pencil didn't break. Blue shift equals moving closer. We'll label that over here, moving closer. Okay, so blue shift is another good term that you should definitely know for any test you're taking on this, and it means that the galaxy or the planet or whatever is moving closer to you, and that could be explained by the Doppler effect. Okay, so galaxy 4. This one is actually an interesting set of spectral lines because this is actually an impossible scenario, because you cannot have part of the spectral lines going towards the violet end of the spectrum and part of them going towards the red end of the spectrum. So this is impossible, and that's because the spectral lines cannot be shifted towards both ends of the spectrum. So we're just going to write that down. So if you were given a question about spectral lines, and this came up as an option, this is obviously not going to be the correct answer because spectral lines cannot be like this. They can't be going towards both ends of the spectrum. So let's just finish writing that down because that is something very important to know. Okay. So spectral lines cannot be shifted towards both ends of the spectrum because that is impossible. You can never have an option like this, and you'd instantly cross that off if you saw it because spectral lines cannot go like that. Okay, so let's go a little bit more in depth on spectral lines, and we're going to start talking about how fast the galaxy is moving away from us. So the easiest way to explain this is the further the spectral lines are shifted away from the standard spectral lines, that's going to mean that the faster it is moving. So, if we look back at galaxy 2, we're going to see that the further these spectral lines are shifted towards the red end of the spectrum, that's going to mean the faster that it is moving away from us. And the closer these are shifted to the standard spectral lines, that's going to mean the slower it is moving. And the same thing with the blue shift as well. The closer it is to the violet end of the spectrum, that's going to mean it's moving closer to us faster. And the closer it is to the standard spectral lines, that's going to mean that it's moving slower. So to finish this all up, we're going to draw a diagram at the bottom just to help understand the wavelengths. So we're going to draw Earth over here. We're going to label it. And we're going to draw 3 planets for now. We don't have to draw galaxies. We're going to draw 2 and 3. So we're going to label that one 1, 2, 3. Doesn't matter about their sizes or distance from Earth, because this is just going to be to understand the wavelengths. So for galaxy 1 up here, we see that it's stationary. So we're going to draw a wavelength that is just the normal wavelength, and that's going to be emitted from a stationary object. So we're going to label that line. Wavelength is the same. So that's going to be the same wavelength that is emitted by any stationary planet or galaxy or whatever, which as far as we know, there is no stationary galaxy in our universe. So now for galaxy 2, we're going to see that galaxy 2 is moving away and it's a redshift. So we're going to draw a longer wavelength because the wavelength is shifted towards the red end of the spectrum, which contains the longer wavelengths. And we're going to label that wavelength is greater. And for galaxy 3, we had a blue shift and it was moving closer to us. So we're going to label a wavelength that is very short because the wavelength is shifted towards the violet end of the spectrum, which contains shorter wavelengths. So we're going to label this line wavelength is less. Okay, so our diagram here, galaxy 1 was stationary, so we gave it the normal wavelength that's emitted by a stationary object, and we labeled that the wavelength is the same. So it's not moving closer or away from us, it's going to stay right there. So the one right here, where the wavelength is greater, because of galaxy 2 had a redshift and it was moving away, since the wavelength is greater, we know that this one is going to be moving away from us. So galaxy 2, it's a redshift, it's moving away. Galaxy 3, we know that there's a shorter wavelength, which means that it's going to be a blue shift, because we're getting shorter wavelengths, and that's going to mean that since the wavelength is less, it's going to be moving towards us. So galaxy 1 is stationary, 2 is moving away because it has a redshift, and 3 is moving towards us because it has a blue shift. So I hope that helped you understand spectral lines a little bit more. So thank you for watching.